My name is Michael. I work for a company called BAM, and I'm a senior platform engineer on the team. And I'll tell you a little bit more about our company, and then a little bit about me, and then I'll get into all the technologies I'd like to talk to you guys about. So this will be like the only formal slide, because I don't want to missay things, because our compliance team could watch it. So Balyasny Asset Management is a diversified global investment firm. And we have over $20 billion in assets under management. And the interesting thing for us, which makes us a little different from some other companies, is almost all of our users are trading teams, which causes us to run some like really fun sorts of scenarios. And as like an example, like something we're currently working on is we have a team that's studying the weather, and they need to be able to submit thousands of GPU-based jobs. But in each cloud provider, you only get a certain amount of capacity. And so like one problem we're trying to solve is like with Airflow, how can you submit jobs to each different cloud provider in different regions and manage to get like 9,000 different GPUs. So I just wanted to point that out because some of the problems we solve are cool. And I just wanted to mention we're hiring, and we hire all sorts of for all sorts of positions, not just the platform team. We have a lot of really cool mathy people and a lot of cool data people. And I noticed some other people didn't do the About Me slide. I always saw it at other tech talks, so I did a quick one. So I've been a platform engineer at BAM for a little more than 5 years, and I designed a lot of our Airflow system with my colleagues. I was a software engineer at Groupon before they chose to lay me off, which was great. And I designed their Airflow system, and I chose to use MWAA for that. And I thought that actually was a nice system. And it has a lot of the similar concepts, just not without Kubernetes. I started my career as a failed trader, and I did that for about 4 years. And the main reason I'm doing this is because my kids think people on YouTube are awesome, and I think it'd be fun for them to see this. Okay, so getting into like the things I really want to talk about, since I somehow created 38 slides, which is not going to be possible in 20 minutes. So I want to point out we run at like pretty big scale. We run on average about 26,000 concurrent CPUs, like when we burst. Sometimes we're going to start bursting into maybe like 100,000 CPUs. We run about 150 terabytes of concurrent RAM usage. And I think that's something that people misunderstand, at least from what I've seen, is that Airflow is actually like extremely good at interfacing with our Kubernetes platform to make this possible. And something that separates us from other companies is Airflow is not just a data tool for us. I always see it get marketed, even at this conference, as sort of like a data orchestration tool, but it's very much not like that for us. Like we have some use cases like that, but then we also have teams doing like really interesting things, and it's more of like a scheduling tool. There's like all sorts of different reasons you might want to schedule a task. It could be because you want to be able to schedule like trades at a certain time. It could be because you want to generate certain signals right before the market closes, where like a signal is basically this idea that like these teams have a universe of stocks, and then they need to be able to kind of make some sort of prediction on returns based on that. So they might have a task that makes a certain set of predictions, and they might have some other tasks that do that too, and then they might have some other tasks that might aggregate those predictions, and then maybe do some sort of optimization. And then we have like a lot of standard use cases too, where like it's the same stuff you would see at any other data engineering sort of presentation with all the ETLs and things like that. So that's really what I want to get across is for us, Airflow is a great scheduling tool. And the main things I think are really good about it is the Airflow UI is something that our users are able to collaborate with. And it's like whoever like first designed the UI did a fantastic job on it. And then the Kubernetes Pod operator really opens up a lot of possibilities for us. So the goals of the presentation, like if I were to get things across to like the targeted audience, I want to be able to show that Kubernetes platform engineers can run Airflow at scale with a platform engineering skill set. Many of us don't know Airflow that well, but yet we're able to run more than 100 environments, and for the most part, pretty successfully. I want to get across to Airflow users, and I'm going to try to spend like a decent amount of time showing why a Kubernetes platform is so awesome for Airflow users, where they can kind of schedule any amount of tasks that they want that use different amounts of resources. And then from a management perspective, I was hoping to get things across to management where like if your company has a Kubernetes platform, you likely have everything in place already where you can just kind of ship productionized Airflow environments. So I wanted to cover like the basic design principles that we have whenever we design anything pretty much. One of the very important things for us is team-based isolation. We can never have one trading team be able to access the data of another trading team. One trading team can't even see what another trading team is doing. If you imagine like a lot of different teams with a similar skill set, Maybe if like you're a trading team and you know another team is successful and you see their DAG names or something like that, maybe you could suddenly figure out what data they're using. And that might be very interesting to you. And so we take it very seriously where one team can never see another team's world. And then the request-based model that we do, I think it's pretty good because each trading team needs to be charged for what they're doing. And each trading team should never have to wait in line behind another trading team. So if one trading team uses 1,000 CPUs, it should never ever be the case that another trading team needs to wait behind them for that to finish so that then they could run their stuff. So I'm going to quickly try to go into all these concepts in 14 minutes. So one thing I thought was interesting is that like a lot of these talks, people seem to take for granted that everyone in the audience knows about Kubernetes and Docker images. But in my experience, it's definitely not the case. So I kind of just want to quickly go through a few slides so that we're all speaking a common language. So Kubernetes at a high level, Kubernetes is very, very good at running containers, and everything in our platform is containerized, whether Airflow tasks or the environment itself. It took us a long time to get to this point. Like 6 years ago, we didn't have a whole lot containerized, and now everything is containerized. And here, I will not spend more than a minute on what a Docker image is, but again, in my experience, like, and I talk to users every day, most people come from these trading teams or even like tech people don't really know what a Docker image is. So I just want to get some basics down. So containers are created from images, and images are just fancy zip files, and they have the application's code and its dependencies in it, and our users are responsible for their images. And these images, from an Airflow purpose, are just fancy zip files that house their scripts that they need their Airflow tasks to ultimately run. And so it was mentioned at one of the talks that maybe this seems like a big overhead to have everybody be responsible for containerizing their stuff and creating these Docker images. But I want to point out that I think in most companies at this point, people have pretty good pipelines to make this easy. So I want to get that across, I guess, where from our user's perspective, there is a bit of a learning curve to start out. But what we end up doing is we provision a repo, it has a Jenkins file in it, it has a Docker file, it has requirements.txt in it, and I think this is standard at most companies now where they don't have to really understand a whole lot about what a Docker image is. They kind of get automatically built. And I also want to point out that it's not that complex because we do this pattern where it's not like you have a Docker image per workflow. Typically, we have a scheduled Docker image per team. And then within the Docker image, like this fancy zip file, all of their logic, all their business logic, the different scripts they might want to run are within it. So in the end, it's not that complicated. And the general selling point of an image is, well, you need an artifact of some kind. Like if you see that people are, if you picture yourself writing any type of code, it needs to end up on your productionized infrastructure somehow. And the general picture in your head to always remember, if you are not that comfortable with Docker images, is it's just a fancy zip file. It has all your stuff in it, and it's easy to kind of ship this around to all sorts of different infrastructure. And then here I just want to point out that images get run as a container, and it's very hard to kind of get this across in a short talk. But I think you could just picture the idea that Kubernetes is basically getting this image onto different infrastructure, and it's like pushing the play button. And then their process will start in its own little world. Okay, so to recap, at this point, we're at the idea that images are fancy zip files. They're a great way to package the tasks run by Airflow tasks, and platform engineers understand them very well. So when people are figuring out how to run their Airflow tasks, how do I run my code, it's actually something a platform engineer is very good at helping with, because they work with Docker images all the time, and then they can help users kind of containerize their stuff. And then a bit more about Kubernetes. A pod is a basic scheduling unit. Pods consist of one or more containers. And for our purposes, every pod is one Airflow task. So I think for our purposes, and in order to not get too long-winded, I just want you guys to understand the idea that everyone is running their Airflow tasks as a pod on one of these nodes. It's just like running their process in its own little world. And as part of the pod, and I want to get this across, a pod is created from a spec, which has all sorts of different information. And importantly, it has these resources, and it has a command to run, and it has the fancy zip file that a user will have created. So a trading team would have their fancy zip file. It has all their scripts in it. And then they would need to request some amount of resources and some command to run. And I wanted to show what a pod spec looks like so that I can kind of try to sell the point of why a platform engineer can support a lot of different teams if they're using the Kubernetes pod operator. Because while a platform engineer may not have seen that many Airflow tutorials or anything like that, they certainly understand what this looks like. Because for years, they've just been looking at specs like this, and the Kubernetes pod operator looks almost exactly the same. So they start to get the hang of the whole game of it. And I would like to kind of get that across. So like if you have a Kubernetes platform, from a platform engineer's perspective, there's nothing different about Airflow versus anything else. So a lot of different services integrate very nicely with this model. And so like if we're using AWS Batch, which is something we've become more excited about, and where somebody might want to submit 80,000 jobs to a platform engineer, that's just like another pod. Whether it's Jenkins, it's just another pod, or whether it's Airflow, it's just another pod. So platform engineers, again, like while they may not know as much advanced Airflow stuff, they're like more than at home with dealing with managing the Kubernetes pod operator. Okay, so I wanted to actually really do a good job, oh shoot, I lost my timer, but I have enough time. I wanted to do a good job explaining the container scheduling game. So I think it's really important for users to understand this, and I explain this to users all the time, and so I'd like to try to do that here. So in terms of the way the Kubernetes scheduler works, it's basically just playing Tetris. And these blocks up here we'll see is like the scheduler trying to look at the different pods that a user submits or Jenkins submits or Airflow submits, and it tries to figure out where to place them. So I want to get across the idea that every single pod and every single VM/computer/node has dimensions. And this is really important for users to understand. I think that abstractions sometimes get in the way and cause people to be less creative. The more they understand these ideas, the more they get out of our platform or any Kubernetes platform. So it's very important in the pod spec for a given task that users include what the resources they require. Because in the end, like if they need 2 CPU and 2 gigs of memory, the scheduler is actually going to look at that very closely, and it's going to figure out what VM has enough space for that. It's not like compute is kind of in thin air or something like that. You have like different nodes/computers with dimensions and a certain amount of space. And so I want to really get this point across. So the scheduler is always looking for pending pods, and then when it sees them, it looks for space of where it can place things. And so if you look here, like the idea to get across is like we have so many Airflow environments, and they're all just submitting tons of pod specs. So pods are constantly accumulating here, and the scheduler is constantly looking at them and figuring out where this is playing Tetris, it's figuring out where they can be. And then the heart of our platform is really the dynamic scaling. And so I really want to get this across. So like 6 years ago, we were tasked with the idea that, or maybe it was 5 years ago, like a teams wanted to be able to run thousands of jobs, and they needed to be able to scale in and out. And so the cluster autoscaler is really like the hero behind the scenes that like really empowers users to run at scale. And the platform engineers don't really have to do a whole lot. They just run the cluster autoscaler, and I'd like to explain how it works. So the general thing to picture is like imagine if you're team B and you submitted a bunch of tasks. And then if your tasks use most of the compute on the cluster, so like from the Tetris playing scheduler's perspective, there's no room for team A's tasks. Something needs to happen, right? Because it's not really fair if team B is able to kind of run their workloads and team A is not. So the cluster autoscaler will look at what's pending, and it has a copy of the scheduler inside of it, and it'll figure out like this is what the scheduler would do. And so even though tons of pods are accumulating and people have to wait a little bit, the cluster autoscaler ends up creating the right sized VMs so that the scheduler can then continue its Tetris game. And so I want to fully sell the point. So then what happens is the scheduler sees that there's enough capacity, and it will start to place all these task pods onto the nodes. And so the users, from their perspective, like they never have to get in each other's way. They're never impacting the performance of each other. And a lot of it is, at the heart of it is the cluster autoscaler. Or maybe your company uses Carpenter, but it's all very similar. And then I wanted to just explain why the cluster autoscaler is also good from a cost efficiency standpoint. So then what happens is people's Airflow tasks start to finish. And so there's no longer any compute that's used on these nodes here. And so the cluster autoscaler will see that, and then it will get rid of them. And so all of our clusters, which I want to show the big picture of, are constantly scaling in and out like in an accordion. And so if you were to picture all of our environments across BAM, where we have like more than 100, we also have more than 50 Kubernetes clusters. And so from our team's perspectives, they will submit jobs to different clusters depending on what their workloads are doing. Like if it's Windows containers that they need, then their Airflow tasks will submit jobs to like an AKS cluster. And then it all scales in the exact same way. Or if it's GPU-based workloads, like they might choose different clusters. Or if it's an on-prem cluster, it's all kind of the same. And at the heart of it is really the cluster autoscaler that is kind of making sure that everything performs well. So another point to make before I move on to how we're running the environments, which I'll have just enough time to do, is users are able to select the compute they want, and it's equally kind of part of like the game of all of this, where in their Airflow tests, they'll specify the resources they need, and then they specify whether they want GPU or whether they want CPU optimized or whether they want memory optimized. And from their perspective, it's just another Kubernetes pod operator call. But then from the scheduler's perspective, it knows like which nodes to scale and which nodes to, well, the cluster autoscaler would, and which nodes to place their workloads on. So to recap, the Kubernetes pod operator runs every task as a pod, and the existing platform enables scalability that perfectly suits job-based workloads. Something I really wanted to comment on is storage. As part of our worlds, we have the reason that our Kubernetes platform is so useful to people is because in addition to kind of providing this scalability, it provides everything a trading team's tasks or any user's tasks need to run. And I feel like in a lot of these talks, no one ever talks about storage. And storage is really at the heart of a lot of things. And like 10 years ago, Netflix did all those talks and they got everyone interested in the S3 model. And I wanted to point out that actually like shared file systems are very big. And it's not that easy to figure out the different isolation or how you're going to mount the different shared file systems into different tasks that are running. And so some of the ones we use are like CIFS and NFS and Lustre. And our teams benefit a great deal from a collaboration standpoint from shared file systems where maybe like their processes will produce a bunch of files and there'll be some artifact and there might be someone on the team like the portfolio manager who would like to be able to go into the Windows Explorer button and just open up like whatever that file system is. Like this person may not want to go into an S3 bucket. And then from a Lustre standpoint, we do run into cases where from a performance standpoint, we need something like Lustre. And so the things we're working on there is this idea that you can have like many, many terabytes of data in your S3 bucket. And then that's like very cost efficient. And then teams can mount Lustre file systems on top of that data. So they'll spin up a Lustre file system, they'll mount it into their tasks, and then they will, from there, tear down the file system. And so it's hard to get all of this across that I wanted to because a lot of it's like more advanced Kubernetes stuff, but I wanted to really get across the idea that from a user standpoint, it's kind of like a set it and forget it thing. It's part of like their Kubernetes pod spec that the platform engineers are very comfortable with. And so they're always able to mount their shares, but never another team's shares. So as part of the namespace, we get the isolation we need. So I wanted to cover in the last 5 minutes then about why like our Kubernetes platform, in addition to empowering users to access everything they need, whether like storage or whether secrets or whether scalability, I wanted to show why like as a platform team, we can run so many environments. So we use the Helm chart that was written by the community, and I think it would be long-winded to explain what a Helm chart is, but the just to picture is it's like a package manager. So if you were to yum install Airflow or pip install Airflow, effectively that's what you're doing, and you're able to install a web server, a scheduler, and a database. And so then at big scale, this is very good for us because we're able to very easily kind of create team-based environments. And it's very important for us that they're separated because we can't have, like let's say like this database for this team has a problem. We can't have like that affect team like 50 stuff. So with the Helm sort of strategy, we're able to create all these different environments and get the isolation we require. And I wanted to show that it's kind of like a simple thing. We've been able to kind of move towards more of an operations heavy area where our operations team, they create this values file, they open a PR, they merge the PR, and then a team gets an environment. And then as part of the environment, they get a lot of stuff automatically, and this comes with Kubernetes. Kubernetes has all these controllers, and if you think about what a controller is, it's basically just like a thermostat, where like if your temperature in your house goes up past 70 and it's supposed to be at 70, then maybe your thermostat would cause your air conditioning to bring down the temperature. And in the same sense, like on a Kubernetes cluster, you have a million thermostats. We have a load balancer thermostat that's always watching for load balancer events, and it will always ensure that a load balancer gets created and configured. We have a DNS thermostat. And so by just merging that one file, all of our teams get all of their environments got automatically set up. Okay, in the last couple minutes, I just wanted to talk from a troubleshooting standpoint. These are the most common questions we get, and I wanted to kind of stress why a platform engineer tends to be able to support this. So we often will get questions about why the task doesn't start, why a task takes X minutes to start, why a task failed, why is the task running more slowly than before. And most of these I wanted to point out is on the platform side. So in terms of why a task didn't start, a lot of times the platform engineers' run books can figure that out, where they They would look to see if like there was an image pull issue or some issue with the pod in terms of why a task takes X minutes to start. It's all kind of like the same idea. In terms of why tasks failed, sometimes this actually does happen on the Airflow side. And in those cases, this is where things can get a little bit more difficult, where the platform engineers might actually need to research different things like concurrency and parallelism and get an understanding of like pool slots to figure out like why something might be queued, or whether like Airflow is just randomly sig terming the task. And on that side, I do think that sometimes like this could be like a gap where like the platform engineer might not be as successful at it. But for the most part, the platform engineers are able to kind of troubleshoot this because it's all on the Kubernetes platform. And then to close out, I wanted to mention some of our challenges. So even though we have like 100 environments or more, it's very hard to do upgrades, which I've heard other people talk about. It's hard to keep up with releases. And then the critical task reliability is really challenging. For us, it's unacceptable if a task fails. And so like even though like the CTO of Amazon a long time ago kind of got me to think differently, where he said that everything fails all the time, our users are not like very accepting of that. And so this is actually like a big challenge, because sometimes with Airflow tasks do fail versus like maybe with like a Linux cron job, you don't really see like obscure things happen. And so this is what led us to like where we're headed. So we had some people think that the idea that some tasks fail at random and we don't understand why, and like platform engineers maybe don't really feel the need to like have that be their focus to figure out why. We started to go more towards like a managed route. So now we have like around 40% on a managed platform, and we have around 60% on ours. And then I wanted to point out we're heading in a batch scheduling strategy where like we tried to get Airflow for teams to run up to 2,000 tasks concurrently, and we weren't able to do that very well. So now we've moved to more of like a batch scheduling platform in addition to Airflow. And then lastly, I wanted to mention from a systematic standpoint, we're trying to solve the problem where teams can run Airflow tasks that can run as close to the close of the market as possible. And there's all sorts of challenges that can happen there, because we can't have like any sort of delays where they miss the market close and miss opportunities. So in the end, I think I had way too many slides, and this is a lesson learned on my side, but I appreciate the chance to talk, so thank you.